Welcome viewers. Good morning everyone. Today is the 7th video lecture on electrostatics. Today's topic is electrostatic potential. For the past 6 video lectures, we had some lectures on the electrostatics, basics of electrostatics, electric field intensity, Coulomb's law, electric field intensity, Gauss law, application of Gauss law, finding electric field intensity using Gauss law, applying Gauss law. We found out the electric field intensity due to infinite long charged conductor. Next, for plane conducting sheet. Next, we have applied Gauss law to find electric field intensity to charged sphere, a solid sphere as well as hollow sphere. Then we applied Gauss law to find out the electric field intensity due to charged cylinder. Now, the next topic, today's topic is the electrostatic potential. So, in this lecture, I'd like to cover the topics like electric potential, potential difference, equipotential surfaces, potential as a function of electric field, conservative nature of electric field, irrotational field. So these are the topics which we are going to deal in this video lecture. Now, let me first see the electrostatic potential. What is electrostatic potential or simply electric potential? Generally, we know when a liquid flows, it flows from a higher region to a lower region. So, in the same way, the charge flows from, in a field, the charge flows from higher potential point to a point at lower potential. So this we can see with the figure shown here. For example, if I take a charge plus Q, the field around it exerted by this charge is, let that be E. The electrostatic field exerted by this charge plus Q is E. Now, let me assume a test positive charge Q naught that is to be moved between points B and A shown in this figure. So, in order to bring this test positive charge between these 2 points, opposing the electrostatic force, opposing the field due to charge plus Q, some work has to be done. So, some external agent has to do some work to bring this unit positive test charge from point B to point A in the electric field produced by the charge plus Q. Now, there occurs a force of repulsion that is shown in the figure. The force of repulsion F is acting in opposite direction to the electric field generated by plus Q. So, charge Q is placed and electric field is produced around it. So, a positive charge, test charge plus Q naught is brought near this charge plus Q. Then a force of repulsion acts that is denoted by F. So, because these two are of positive charges, now some work is to be done. So, anyhow the force is acting in opposite direction. So, in order to bring this test positive charge near point A from B, some work has to be done by an external agent. So, the work done in bringing this test charge from one point to another point in an electric field to the magnitude of the test charge is defined as the electric potential difference between these 2 points shown in the figure as A and B. So, in order to overcome the repulsive force, some work is to be done on plus Q naught. This is test positive charge. So, in order to bring it from point B to point A in the field of plus Q, so in order to overcome the repulsive force, some work has to be done in bringing this test positive charge plus Q naught from point B to point A. Some work is to be done. So the ratio of this work done to the magnitude of the test charge gives you the potential difference between the 2 points A and B. Now from figure, the potential difference, for example, if the potential at point A is VA and at point B, if the potential is VB, then the potential difference between A and B is VA minus VB, that is equal to W by Q naught. So W is the work done in bringing this test charge from point B to point A, and Q naught is the magnitude of the test charge. If B is infinity, then the potential at point B is, so the point B is some at infinity distance, then in order to bring this charge from infinity to point A, some work is to be done there. That the potential is defined as here VA is equal to W by Q naught. In general, I can say that the potential V is equal to W by Q. So we can define this electric potential as the electric potential at a point in the electric field. The electric potential at a point in the electric field can be defined as the work done by an external agent in bringing a unit positive test charge from infinity to that point against electric force of the field. So here what we are saying, we are defining electric potential like the electric potential at any point in the electric field can be defined as the work done by an external agent in bringing unit test positive charge from infinity to that point against the force of electric force of the field. So here just now we have seen that the electric potential is given by V, it is denoted by capital V, and this V is equal to W by Q. W is the work done and Q is the charge. Now here the SI units are, if work is, the SI unit of work is joule and for charge it is coulomb, then the SI unit of potential is joule per coulomb, or that is written as that the unit of that electric potential is said to be volt. So it is denoted by V. So we can define 1 volt as the work, if the work done in bringing a unit positive charge from infinity to a point against the electric force of the field if the work done is 1 joule, then I can say that the potential, electric potential at that point is 1 volt. Now let me say this, electric equipotential surfaces. What are equipotential surfaces? Equipotential means points having same potential. Equi means same. So the surfaces whose at every point on the surface the potential is same, then we say that it is equipotential surface. So the locus of all points which have the same electric potential is called equipotential surface. So the locus of all points which have the same electric potential is called an equipotential. So here, for example, if a charge is brought into an equipotential surface, what is the work done in bringing the charge from one point to another point? So the work done will be 0, because equipotential surface, the potential is same at every point. So in bringing the charge from one point to another point, there is no potential difference. So the potential at every point is said to be same. Therefore, there is no potential difference. Hence, if the potential difference is 0, the work done W by Q is 0. Hence, the work done on that charge is 0. So, the work done on a charge placed in an equipotential surface is 0. And we can also say that the electric lines of force at every point of the equipotential surface are perpendicular to the surface. See here in the figure, the electric lines of force in the first figure, it is uniform electric field. So the electric lines are shown in blue with arrow marks. It is a uniform electric field. There the lines of force are parallel to each other, and the lines of force at every point of equipotential surface are seen to be perpendicular to the surface. Here the equipotential surfaces are shown with red. They are shown with red. So if you see this type of figure 1, the equipotential surfaces are shown with red dotted lines, and the electric lines of force are shown by blue lines. Now the lines of force at every point of the equipotential surface are normal to the surface. So the electric field is normal to the, at every point of the equipotential surface, it is normal to the surface. So the electric field and the equipotential surface are here perpendicular. Now in the second case, figure 2, it is a family of concentric spheres. Concentric spheres means having the same center. So the electric lines of force are radially outwards. They are shown in blue lines, and the equipotential surfaces are shown in red dotted lines. So these are we can say that equipotential surfaces are shown in this figure. This is uniform electric field, that is the electric field due to a sphere. Now we can say that here the equipotential surface is perpendicular to the lines of force. And we can also say that the locus of all the points have the same electric potential. And we can also say that the work done on the charge in an equipotential surface is 0. So these are the some of the properties of equipotential surfaces. Now let us see the potential, how the potential varies with electric field. So the potential as a function of electric field. Now see in this figure, E is an electric field generated by some static charges, and here we are at point B, in between point A and B. Some test charge Q naught is to be moved from B to A. So in order to move this test charge from B to A, here we are assuming this test charge Q naught in this electric field E. Now the distance between, let the distance between these 2 points is R. Now the charge Q naught, let it be moved through a small distance dr. So the work done in moving a charge Q naught through this small distance dr by some external agent is given by, we know that work is nothing but the scalar product of force and displacement. So if the charge has to be displaced a small amount dr, then the work done, the small amount of work done dw by some external agent is given by dw is equal to F dot dr. So that is equal to, here I have written in equation number 1 as minus Q naught E dot dr. It is dr. So why minus? So here the force is acting, a repulsive force is acting on the charge, test charge Q naught, to bring it into the field generated by some static charges. So in order to move this test charge between points A and B, the force is on the test charge is minus Q naught E. So it is dw is equal to minus Q naught E dot dr. So let this be equation number 1. Now the total work done in bringing the charge from point B to point A is WBA. So this charge Q naught is brought to point A from B, then some external work is done by an external agent, then that work done is shown as WBA. So it is given by WBA is equal to, just now we have taken this dw as the work done is F dot dr. F is equal to minus Q naught E, because a repulsive force is acting on the test charge in the field set up by the static charges E, and in order to move a small distance dr, the work done is minus Q naught E dr. Now the total work done will be integration of minus Q naught E dot dr from B to A. We have to integrate the total work done in bringing this Q naught charge from B to A. So we have to integrate it. So in order to bring for a small distance dr, dw is equal to F dot dr. In order to calculate the total work done, we have to integrate it from B to A. So WBA is equal to integral B to A minus Q naught E dot dr, that is equal to minus Q naught is a constant, so integral B to A E dot dr. But we know that the potential difference is equal to WBA by Q naught. It is the ratio of the work done to the magnitude of the test charge gives you the potential difference. So the potential difference is written as VA minus VB is equal to WBA by Q naught. Therefore, potential difference between 2 points A and B will be VA minus VB, that is equal to minus integral B to A E dot dr. Or the potential difference can be written like this, and if B is at infinite distance, so that is VBA is equal to VA minus VB is equal to minus integral B to A E dot dr. So if B is at some infinity distance, then VB is equal to 0. The potential at infinity is treated to be 0. Therefore, the potential at point A will be equal to minus integral E dot dr. So we can say that the electric field is, the electric potential is the line integral of electric field intensity. So the electric field intensity and potential, or they have a relation like potential is equal to line integral of electric field. So the electric potential at a point in the electric field can be expressed as a line integral of the electric field. So this is the one of the relations between electric potential and electric field. Here we have to remember that electric field intensity is a vector quantity and electric potential is a scalar quantity. Next, conservative nature of electric field. So here the electric field, not only electric field, any field, if F is said to be a field F is said to be conservative, then the curl of that field is to be equal to 0. We have studied this conservative nature of this force in the first year BSc Central Forces. So the condition for the conservative nature of the force is any field is that the curl of that field is 0. Now if we consider in the figure 1, if we consider a positive charge plus Q at O at point at origin, then the at point P, if electric field intensity is E at a distance r from this charge, we are considering a point P at a distance r from O. At point O, we are considering the positive charge plus Q. And now the electric field intensity is given by 1 by 4 pi epsilon naught Q by r square. Now if we consider any two arbitrary points in this, then A and B are any two arbitrary points in the space. Now I can say that the position vectors of A is RA, and if RB is the position vector of point B, then I can say that the electric field intensity is integral A to B E dot dr is equal to integral 1 by 4 pi epsilon naught Q by r square dr. We know that. We know that electric field intensity is 1 by 4 pi epsilon naught Q by r square. So if you want to know the potential difference between A and B, then A and B are any two arbitrary points. Then if RA and RB are the position vectors of A and B, then I can say that the integration of E dot dr. So this is nothing but the potential difference between A and B gives you as equal to this equation integral A to B 1 by 4 pi epsilon naught q by r square dr, or this is 1 by 4 pi epsilon naught q by 1 by r square. It is integration of 1 by r square is minus 1 by r. So it is substitution of upper and lower limits. Instead I am substituting the lower and upper limits. So it is integral A to B E dot dr is equal to 1 by 4 pi epsilon naught q by RA minus q by RB. So here these are the position vectors. RA and RB are the position vectors just now we have discussed. And if A and B are at same point, so here we are saying that A and B are at 2 points, different points, arbitrary points, and they are having the position vectors RA and RB. Now if both are at one point, then the position vectors will be same. So RA and RB will be merging. So that comes to be a closed line integral over a closed curve. So integral E dot dr is equal to, now it is 0. So according to Stokes theorem, so if A and B 2 points are equal, then their position vectors will be equal. Then the closed curve along E dot dr, so the curve along the potential difference will gives you the value to be 0. So both are at the same point, then there is no potential difference. Therefore integral E dr becomes equal to 0. No potential difference. So according to Stokes theorem, integral E dot dr is equal to integral over a surface del cross E curl E dot ds is equal to 0. Stokes theorem in vector analysis says that the line integral is equal to the curl of any force into ds. So if line integral E dot dr is equal to 0, according to Stokes theorem, line integral E dot dr is equal to surface integral curl E dot ds is equal to 0. Then if this is 0, then curl E dot ds is equal to 0. Therefore curl E is equal to 0. We say that if curl E is equal to 0, then such type of the force or field is known as conservative. So here we say that an electric, this is how we prove that the electric field is a conservative field, because we are assuming an electric field at point P due to a positive charge plus Q, and we have found out the value of electric field intensity as 1 by 4 pi epsilon naught q by r square. Then we are assuming 2 points A and B. We found out the potential difference between these 2 points. Just now we have derived the relation between the potential difference and the electric field intensity to be the line integral of electric field intensity is nothing but the potential. So electric potential. Therefore, I am intending to find the potential difference between 2 points A and B. So the potential difference between the 2 points is nothing but the integration of E dot dr where these 2 points are at a distance of RA and RB. Now the potential difference is shown to be as equal to integration of A to B 1 by 4 pi epsilon naught q by r square dr. So here the integration of E dot dr gives you the potential. If I assume to be, I found out this value, and if I assume to be the 2 points to be at one point, then there is no potential difference. So integral E dot dr is taken to be as equal to a closed curve. So it is taken to be as equal to 0. Then according to Stokes theorem, line integral is equal to surface integral. Line integral E dot dr is equal to surface integral of curl E dot ds is equal to 0. So if this is 0, then curl E is equal to 0. We say that E is conservative. So E is conservative in the sense there is no change in the electric field. So the field is said to be conserved. So for example, curl in the sense, what is the meaning of curl? Curl means rotation. If there is no curl, means curl of an electric field, we are saying that it as equal to 0. So if curl of electric field is said to be 0, then there is no rotation. So we can say that the electrostatic field is an irrotational field. So if curl of any field is 0, then we say that that field is irrotational. So there is no rotation. If there is no curl, there is no rotation. So it is said to be irrotational. So that is what is given over here also. So curl E is equal to 0, then curl of a vector is if it is 0, then there is no rotation attached with the electric field over here, and hence E is said to be irrotational. So our electric field is an irrotational electric field. Now you can better understand this conservative nature of electric field by means of this problem. If a field vector has components Ex is equal to 3xy, Ey is equal to x square minus y square, and Ez is equal to 2x, is it possible that E is an electrostatic field? So can you say that, this question is, can you say that the electric field E is conservative? Is it possible to say that this field is electrostatic field? So the question is, can you say that the components, the field with such type of components is electrostatic or not? In order to say that it is an electrostatic field, we have to prove that it is a conservative field. If this is conservative, if del cross E is equal to 0, then it is said to be conservative. So if it is not 0, then it is not conservative. Then we can say that the electric field associated with this type of components is not conservative. For that, we have to find the curl of that electric field. I can say that this electric field intensity as equal to 3xy I plus x square minus y square j plus 2x k. Now if these are the three components, I can write electric field intensity E as equal to EXI plus EYJ plus EZK. So that is what I am saying. So the curl of that vector, curl E is equal to, we have to find the curl by means of this method IJK dou by dou x. Del is I dou by dou x plus j dou by dou y plus k dou by dou z is del, operator del. So if you find the value of del cross E, I can write like this. So the components of x component can be written under I, j, and y component under j, and z component under k respectively. Now after calculation, we have to we come across like the vector as found to be minus 2j minus xk. So you got a vector over here. So del cross curl E is not found to be 0. So it is not equal to 0. If curl E is not 0, that field is not a conservative field. So we say that E is not a conservative. Right? So next let us see this. Prove that E is equal to a component E is given as, the vector E is given as 2xi plus 2yj plus 3zk, and you have to show that this as a electrostatic field. In order to show that a given field is an electrostatic field, we have to prove that curl of E is equal to 0. So if curl of that vector is 0, then we can say that this is an electrostatic field. So del cross E we are finding, and here also we have made a calculation This you know pretty well. So I have illustrated these examples to show you to better understand the concept of conservative nature of electric field. So here we found out to be del cross E is equal to 0. Hence we say that E is an electrostatic field. The if the curl E is equal to 0, we say that electrostatic field is the field is conservative. So if the field is conservative, that field is nothing but electrostatic field. So in that way we can show this. Thank you.